In this video, we will review triangle trigonometry. The starting point of trigonometry is the study of right triangles. A right triangle is a triangle in which one of the angles is 90 degrees, also known as a right angle, and the other two angles are acute angles, which add up to 90 degrees. An important relation among the side lengths of a right triangle is the Pythagorean theorem, which states that a squared plus b squared equals c squared. As an example, let's find the value of b in the given triangle. By the Pythagorean theorem, we have b squared plus 8 squared equals 12 squared. Simplifying, we get b squared plus 64 equals 144. Subtracting 64 from both sides, we get b squared equals 80. Therefore, b equals the square root of 80, which means b is the square root of 16 times the square root of 5, which means that b is 4 times the square root of 5. In a right triangle, if we label one of the angles theta, then the side opposite of theta is called the opposite side of the triangle. The side adjacent to theta is called the adjacent side of the triangle, and the side opposite of the right angle is called the hypotenuse of the triangle. Given these terms, we can then define the trigonometric ratios of an angle theta. The sine of theta is defined to be the length of the opposite side divided by the length of the hypotenuse. The cosine of theta is defined to be the length of the adjacent side divided by the length of the hypotenuse. The tangent of theta is defined to be the length of the opposite side divided by the length of the adjacent side. Similarly, the cosecant of theta is hypotenuse over opposite, the secant of theta is hypotenuse over adjacent, and the cotangent of theta is adjacent over opposite. The mnemonic device SOHCAHTOA is useful for remembering the trigonometric ratios for sine, cosine, and tangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. In the next example, let's find the value of cosine of theta in the given triangle. First, recall that the cosine of theta is equal to the adjacent side over the hypotenuse. We notice that the adjacent side in this triangle is not given, so first we have to solve for it. By the Pythagorean theorem, we have b squared plus 2 squared equals 6 squared. Simplifying, we get b squared plus 4 equals 36. Subtracting 4 from both sides, we get b squared equals 32. Therefore, b is the square root of 32, which we can write as the square root of 16 times the square root of 2, which means that b is 4 square root of 2. Finally, we see that cosine of theta equals the adjacent side length, which is 4 square root of 2, over the hypotenuse, which is 6, which simplifies to 2 square root of 2 over 3. For this next triangle, let's find the value of cotangent of theta. Recall that cotangent of theta is adjacent over opposite. Now, theta is in a different location compared with the previous triangle. For this triangle, and for this angle theta, the adjacent side would be the side with length 3, and the opposite side would be this side, which we'll label b. Again, this side length is unknown, so we'll have to solve for it. We have b squared plus 3 squared equals 7 squared, which means b squared plus 9 is 49. which means b squared is 40. Therefore, b is the square root of 40, which we can write as the square root of 4 times the square root of 10, which means that b is 2 square root of 10. Finally, we have that cotangent of theta is the adjacent length, which is 3, divided by the length of the opposite side, which is 2 square root of 10. If we choose to rationalize this number, then we would multiply by the square root of 10 over the square root of 10, which gives us 3 square root of 10 over 20. A useful application of trigonometric ratios is to find the exact value of the length of a side of a triangle given the measure of one angle in the triangle and one side length in the triangle. In this case, we need to find the trigonometric ratio which relates x to 3 relative to the angle 37. Relative to this angle, x is the opposite side and 3 is the adjacent side. So tangent is the ratio we want to use. Specifically, we have the tangent of 37 degrees equals the opposite over the adjacent, which is x over 3. And multiplying both sides by 3, we can solve for x. We get 3 times the tangent of 37 degrees equals x. This expression represents the exact value of x. And if we put this into a calculator, we get that x is approximately 2.26. In our final example, we will suppose that theta is an acute angle in a right triangle, and we'll suppose that the secant of theta is 2 square root of 7 over 5. Given this information, we want to find the cosecant of theta. To do this, let's first draw a right triangle. Now, since secant of theta is 2 square root of 7 over 5, and we know that the secant of theta is the hypotenuse over the adjacent side, we can label two sides of this triangle. Relative to theta, the hypotenuse will label 2 square root of 7, and the adjacent side will have length 5. Since the cosecant of theta is hypotenuse over opposite, and the opposite side of theta is unknown, we'll have to solve for it. We'll label it b, and we get b squared plus 5 squared is 2 square root of 7 squared. Simplifying, we get b squared plus 25 is equal to 28, which means that b squared is equal to 3, which means that b is equal to the square root of 3. Therefore, we get that the cosecant of theta is 2 square root of 7 over the square root of 3. And if we choose to rationalize, we'll multiply by the square root of 3 over the square root of 3, which gives us 2 times the square root of 21 over 3. This concludes our review of triangle trigonometry. In this video, we will review trigonometric functions and the unit circle. First, we need to discuss the concept of similar triangles. Recall that two triangles are similar if they have congruent angles. For example, in the triangle shown, each side length in the larger triangle is twice the length of the corresponding side in the smaller triangle. Because of this proportionality, a given trigonometric ratio in one triangle will be equal to the same trigonometric ratio in the other triangle. For example, if we label these congruent angles theta, then the tangent of theta in the first triangle, which is 3 over 4, is equal to tangent of theta in the other triangle. Therefore, when computing trigonometric ratios for a given angle, one could first rescale the triangle to a smaller or larger size. In particular, if we rescale the triangle so that the hypotenuse has length 1, that is, if we multiply each of the side lengths of the original triangle by 1 over the hypotenuse, then we obtain simpler representations of the trigonometric ratios. Specifically, if we label the rescaled legs of the triangle x and y, then we obtain the following formulas. Sine of theta is y over 1. Cosine of theta is x over 1. Tangent of theta is y over x. Cosecant of theta is 1 over y. Secant of theta is 1 over x. And cotangent of theta is x over y. If we introduce the following coordinate system, then this vertex of the triangle lies on the circle of radius 1 centered at the origin. This circle is called the unit circle. From this point of view, the trigonometric ratios for a given angle theta can be determined from the coordinates of the point on the unit circle corresponding to theta. For example, tangent of this angle theta is y over x, where x and y are the coordinates of this point on the unit circle. Now let's identify a few key points on the unit circle which are referred to frequently in trigonometry. First, when theta is 45 degrees, we get the point square root of 2 over 2, comma, square root of 2 over 2. To see why these are the correct coordinates, recall from geometry that these two side lengths are the same since these two angles are the same. Therefore, by the Pythagorean theorem, we have x squared plus x squared equals 1 squared. Simplifying, we get 2x squared equals 1. Therefore, x squared equals 1/2, which means that x is the square root of 1/2. Simplifying, we get x is 1 over the square root of 2. And then rationalizing this denominator, we get x is the square root of 2 over 2. So we find that the coordinates of this point on the unit circle are square root of 2 over 2, square root of 2 over 2. Next, when theta is 30 degrees, we get the point square root of 3 over 2, 1/2. These coordinates follow from the fact that in a 30, 60, 90 triangle, the side opposite of the 30-degree angle is 1/2 of the length of the hypotenuse, and the side opposite of the 60-degree angle is square root of 3 times the length of the shortest side, which is 1/2 in this case. 1/2 times the square root of 3 is square root of 3 over 2. By symmetry, the angle theta equals 60 degrees corresponds to the point 1/2 square root of 3 over 2. The advantage of the unit circle point of view is that we now have a way to define trigonometric ratios for angles larger than 90 degrees. For a given angle, we find the corresponding point x, y on the unit circle and compute the trigonometric ratios using these coordinates. For example, the angle 135 degrees corresponds to the point minus square root of 2 over 2, square root of 2 over 2. Therefore, the tangent of 135 degrees equals the y-coordinate of this point, square root of 2 over 2, divided by the x-coordinate of this point, which is minus square root of 2 over 2. And this simplifies to minus 1. So the tangent of 135 degrees has a value of minus 1. In this way, we see that each trigonometric ratio can be viewed as a function which takes an angle as the input and returns a real number as the output. We will discuss this idea in detail in the next video. The key points on the unit circle are summarized in the following diagram. First, the multiples of pi over 6 divide each quadrant into thirds. The multiples of pi over 4 are located at the midpoint of each quadrant as well as the quadrantal angles. The quadrantal angles are the angles 0, 90 degrees, 180 degrees, and 270 degrees. We refer to this as quadrant 1 of the unit circle. This is quadrant 2. This is quadrant 3. And this is quadrant 4. In trigonometry and calculus, it is more common to use units of radians instead of degrees when measuring angles. For a given angle, if we measure the arc length subtended by this angle on the unit circle, then that value is the radian measure of the angle. The length of this arc is approximately equal to 1, so this angle would be approximately 1 radian, which is roughly 57 degrees. Since the total circumference of the unit circle is 2 pi, we see that 2 pi radians equals 360 degrees. If we divide both sides by 2 pi, we see that 1 radian equals 180 over pi degrees. On the other hand, if we divide both sides by 360, we see that 1 degree equals pi over 180 radians. These relations will help us convert from units of degrees to radians and vice versa, as the following examples illustrate. First, we'll convert 240 degrees to radians. To convert to radians, we'll multiply by pi over 180. We get 240 degrees multiplied by pi over 180 equals 240 over 180 times pi, which simplifies to 4 pi over 3. This shows that 240 degrees is equal to 4 pi over 3 radians. Next, let's convert 5 pi over 6 radians to degrees. To convert to degrees, we'll multiply by 180 over pi. In this case, we get 5 pi over 6 times 180 over pi. The pi's will cancel, and 6 goes into 180 30 times. This gives us a result of 150 degrees. Now let's practice evaluating trig functions using the unit circle. In this example, we want to find the value of sine of 5 pi over 4 radians. First, recall that sine of theta is opposite over hypotenuse, which from the new point of view is just equal to the y-coordinate of the corresponding point on the unit circle. So we need to locate the point corresponding to the angle 5 pi over 4 radians on the unit circle. On the unit circle, corresponding to the angle 5 pi over 4, we find the point minus square root of 2 over 2 minus square root of 2 over 2. To find the sine of this angle, we have to take the y-coordinate of this point. Therefore, the sine of 5 pi over 4 is equal to minus square root of 2 over 2. In our final example, let's evaluate the cotangent of 11 pi over 6. Recall that cotangent of theta is equal to the adjacent side length over the opposite side length, which in terms of the unit circle is x over y. So as in the previous example, we'll locate the angle corresponding to 11 pi over 6, and we'll find its coordinates, and from those coordinates we'll determine the cotangent of theta. 11 pi over 6 radians corresponds to 330 degrees, which we find in quadrant 4 of the unit circle. Therefore, the cotangent of 11 pi over 6 is equal to the x-coordinate of this point, square root of 3 over 2, divided by the y-coordinate of this point, which is minus 1/2. And this simplifies to give us minus square root of 3. So we find that the cotangent of 11 pi over 6 is equal to minus square root of 3. This concludes our review of trigonometric functions in the unit circle. In this video, we will review trigonometric functions in their graphs. Previously, we learned how to evaluate a trigonometric function using the unit circle. For example, the sine of an angle is defined to be the y-coordinate of the associated point on the unit circle. Therefore, the sine of 60 degrees is square root of 3 over 2. The sine of 135 degrees is square root of 2 over 2. The sine of 210 degrees is negative 1/2. And finally, the sine of 330 degrees is also negative 1/2. We can even define the sine of an angle which is larger than 360 degrees. For example, 420 degrees is 360 degrees plus 60 degrees. We find the point on the unit circle corresponding to 420 degrees by starting at 0 degrees, then going 360 degrees counterclockwise, followed by another 60 degrees counterclockwise. This takes us to the point 1/2 square root of 3 over 2, which is the same as the point corresponding to 60 degrees. Therefore, sine of 420 degrees equals sine of 60 degrees, which is root 3 over 2. Adding another 360 degrees to 420 degrees, we again arrive at the same point on the unit circle. So sine of 780 degrees is also square root of 3 over 2. On the other hand, negative angles are associated with clockwise rotation. For example, negative 30 degrees corresponds to the same point as 330 degrees. So sine of negative 30 degrees equals minus 1/2. Subtracting another 360 degrees from negative 30 degrees, we get to minus 390 degrees, which also has a sine value of minus 1/2. In this way, we can view sine theta as a function whose domain is all real numbers. Let's investigate the graph of the sine theta function. For each angle along the horizontal axis, we'll compute the y value using the unit circle. When theta equals 30 degrees, or pi over 6, the associated y value is 1/2. When theta equals 90 degrees, or pi over 2, the associated y value is 1. When theta is 180 degrees, or pi, the associated y value is 0. From this point, we enter quadrant 3, and the corresponding y values become negative until we reach the starting point, which corresponds to 2 pi radians. From there, we see that we begin to repeat the same values as before. By this process, we produce the graph of the sine function. Because the graph repeats after the angle 2 pi, we say that this function is periodic with period 2 pi. The domain of the sine function is all real numbers, and the range of the sine function is the closed interval -1 to 1. The graph of the cosine function has essentially the same shape. Note that when theta equals 0, the value of cosine is 1. Therefore, this graph has a y-intercept of 1. The cosine function is also periodic with period 2 pi. Its domain is also all real numbers, and its range is also the closed interval -1 to 1. If we superimpose the graphs of sine and cosine, we see that the cosine function is simply a horizontal translation of the sine function. One identity that expresses this relationship is sine x equals cosine of x minus pi over 2. That is, if we take the cosine graph and we shift it to the right by pi over 2 units, we obtain the sine graph. The graph of the tangent function requires a more careful analysis. Notice that when theta equals pi over 2, the tangent of theta is 1 divided by 0, which is undefined. Similarly, when theta equals 3 pi over 2, the tangent of theta is minus 1 divided by 0, which is also undefined. These undefined values will correspond to vertical asymptotes in the graph of tangent. Notice that the vertical asymptotes are located at the odd multiples of pi over 2, whereas the x-intercepts of the tangent graph are located at the multiples of pi. Another key point on the graph is this point, which corresponds to theta equals pi over 4, where the tangent has a value of 1. In contrast with the sine and cosine function, notice that the period of the tangent function is pi. The domain of the tangent function will exclude all odd multiples of pi over 2, and the range of the tangent function will be all real numbers. Next, we will analyze the graph of the cotangent function. Observe that the cotangent of theta is undefined when the y-coordinate is 0. This corresponds to the angles of 0 and pi on the unit circle. Therefore, the cotangent function will have asymptotes at the multiples of pi, and it will have x-intercepts at the odd multiples of pi over 2. Like the tangent function, the period of cotangent is pi. The domain of cotangent excludes all multiples of pi, and the range of cotangent is all real numbers. Continuing with the cosecant function, we see that cosecant of theta is also undefined when the y-coordinate is 0. This means that the graph of cosecant of theta will also have asymptotes at the multiples of pi. Here it's useful to note that cosecant of x is 1 over sine of x. So let's sketch the graph of sine of x as a point of reference. Notice that for this portion of the sine graph, where the values are between 0 and 1, the reciprocal of these y values will be greater than or equal to 1. For this portion of the sine graph, where the values are between 0 and minus 1, the reciprocal of these y values will be less than or equal to minus 1. If we also take into account the location of the asymptotes at the multiples of pi, we see that these blue curves represent the graph of cosecant of x. Observe that cosecant of x has period 2 pi, its domain excludes all multiples of pi, and its range is the set of all real numbers between minus infinity and 1, union the real numbers between 1 and infinity. Finally, we'll analyze the graph of the secant function, which will be similar to the graph of the cosecant function. Observe that secant of theta is undefined when the x-coordinate is 0. This corresponds to the angles pi over 2 and 3 pi over 2 on the unit circle. Therefore, the secant function will have asymptotes at the odd multiples of pi over 2. Since secant x is 1 over cosine x, we'll draw the graph of cosine x in red as a point of reference. Taking into account the location of the asymptotes at the odd multiples of pi over 2, and the fact that the reciprocal of a y value, which is less than 1, results in a value which is greater than 1, we obtain the graph of the secant function. Finally, observe that the period of the secant function is 2 pi, its domain excludes the odd multiples of pi over 2, and its range is the same as the cosecant function, which is minus infinity to minus 1, union 1 to infinity. This concludes our review of trigonometric functions and their graphs. In this video, we will review inverse trigonometric functions. One motivation for studying inverse trigonometric functions is to learn how to solve problems of the following type. Given the lengths of two sides of a right triangle, find the measure of one of the unknown angles. In this case, we know that theta must satisfy the equation sine theta equals 3/5. As we will discuss shortly, there are many angles theta which satisfy this equation. However, there is only one acute angle with a measure between 0 and pi over 2 radians, which solves this equation. This value will be denoted by sine inverse of 3/5. In other words, this expression represents the exact value of theta, which is approximately 0.64 radians, or 37 degrees. This notation suggests that the sine function is an invertible function. However, this is not the case since the graph of sine x fails the horizontal line test. For example, if we graph the horizontal line y equals 3/5, we find infinitely many angles for which the sine function attains the value 3/5. This means that the equation sine x equals 3/5 has infinitely many solutions. The solution corresponding to this angle between 0 and pi over 2 is somehow the most natural solution, since it is the relevant value in the context of triangle trigonometry. That is, theta equals sine inverse of 3/5 refers to this particular angle. On the other hand, if we consider the equation sine x equals negative 3/5, then there is no natural choice for which angle sine inverse of negative 3/5 should represent. The simplest choice appears to be either this angle, which is located in quadrant 4 on the unit circle, or this angle, which is located in quadrant 3 on the unit circle. The rule that we will follow is to always choose the angle in quadrant 4 when evaluating the sine inverse of a negative number. That is, sine inverse of negative 3/5 represents this particular angle. The advantage of this choice is that it makes the inverse sine function continuous. That is, if we restrict the domain of the sine function to the closed interval minus pi over 2 to pi over 2, which correspond to quadrants 1 and 4 on the unit circle, then the resulting function passes the horizontal line test and therefore has an inverse function. The resulting inverse function is called the inverse sine function. To obtain the inverse function graphically, we reflect the restricted sine graph across the line y equals x, which results in the graph of sine inverse. Note that the domain of sine inverse of x corresponds to the range of sine of x, which is the closed interval minus 1 to 1. On the other hand, the range of the inverse sine function corresponds to the restricted domain of the sine function, which was the closed interval minus pi over 2 to pi over 2. Let's consider two examples where we look at this from the point of view of the unit circle. In the first example, let's find the value of sine inverse of square root of 3 over 2. Remember that this expression represents an angle, so let's call it theta. This means that sine theta equals the square root of 3 over 2. There are two angles theta whose corresponding points on the unit circle have a y-coordinate of square root of 3 over 2. One when theta is pi over 3, and the other when theta is 2 pi over 3. However, since we're finding sine inverse of a positive number, we will always choose the angle in quadrant 1, which is pi over 3. Therefore, sine inverse of square root of 3 over 2 equals pi over 3. Next, let's evaluate sine inverse of negative 1/2. We'll call the value of this expression theta. Therefore, sine theta equals negative 1/2. There are two angles theta whose corresponding points on the unit circle have a y-coordinate of negative 1/2. One when theta is negative pi over 6, and the other when theta is 7 pi over 6. However, since we're evaluating sine inverse of a negative number, we will always choose the angle in quadrant 4, which is negative pi over 6. Therefore, sine inverse of negative 1/2 equals negative pi over 6. Note carefully that we called this angle negative pi over 6 and not 11 pi over 6. This distinction is important when working with inverse trig functions. Next, to define the inverse cosine function, we will restrict the domain of cosine to the closed intervals 0 to pi, which corresponds to quadrants 1 and 2 on the unit circle. Similar to the previous case, this selects a continuous piece of the graph of the cosine function, which passes the horizontal line test, and represents the full range of cosine values from minus 1 to 1. The inverse of the cosine function with domain restricted to the interval 0 to pi is called the inverse cosine function and is shown in the following graph. Note that the domain of cosine inverse of x corresponds to the range of cosine x, which is the closed interval -1 to 1. On the other hand, the range of the cosine inverse function corresponds to the domain of the restricted cosine function, which was the closed interval 0 to pi. In other words, the range of cosine inverse corresponds to quadrants 1 and 2. In the next example, let's compute the cosine inverse of -1/2. First, we'll call this expression theta. Therefore, cosine theta equals -1/2. There are two angles theta whose corresponding point on the unit circle has an x-coordinate of -1/2. One is theta equals 2 pi over 3, and the other is theta equals 4 pi over 3. However, since we're finding the cosine inverse of a negative value, we will always choose the angle in quadrant 2, which is 2 pi over 3. Therefore, cosine inverse of -1/2 equals 2 pi over 3. Next, to define the inverse tangent function, we will restrict the domain of tangent to the open interval -pi over 2 to pi over 2, which corresponds to quadrants 1 and 4 on the unit circle. As in the previous cases, this selects a continuous piece of the graph of the function, which passes the horizontal line test and represents the full range of tangent values from -infinity to infinity. The inverse of the tangent function with domain restricted from -pi over 2 to pi over 2 is called the inverse tangent function and is shown in the following graph. Note that the domain of the inverse tangent function corresponds to the range of the tangent function, which is the interval -infinity to infinity. On the other hand, the range of the inverse tangent function corresponds to the restricted domain of the tangent function, which was the open interval -pi over 2 to pi over 2. That is, the range of inverse tangent corresponds to quadrants 1 and 4. In the next example, let's evaluate tan inverse of -1. First, let's call this expression theta. This means that tangent of theta equals -1. To find theta, note that there are 2 points on the unit circle where the quotient of the y-coordinate and the x-coordinate is -1. One when theta is 3 pi over 4, and the other when theta is -pi over 4. However, since we're computing tan inverse of a negative number, we will always choose the angle in quadrant 4, which is -pi over 4. Therefore, tan inverse of -1 equals -pi over 4. Next, to define the inverse cotangent function, we will restrict the domain of the cotangent function to the open interval 0 to pi, which corresponds to quadrants 1 and 2 on the unit circle. Again, this selects a continuous piece of the graph of the function, which passes the horizontal line test and represents the full range of cotangent values from -infinity to infinity. The inverse of the cotangent function restricted to this domain is called the inverse cotangent function and is shown in the following graph. Observe that the domain of the inverse cotangent function corresponds to the range of the cotangent function, which is the interval minus infinity to infinity. On the other hand, the range of the inverse cotangent function corresponds to the domain of the restricted cotangent function, which is the interval 0 to pi. In other words, the range of the inverse cotangent function corresponds to quadrants 1 and 2. In the case of the secant function, we will not be able to select one continuous piece of the graph which represents the full range of secant values. This is because the range of secant excludes all values between -1 and 1. However, since secant x is 1 over cosine x, it is natural to restrict the secant function to the same quadrants as cosine, namely quadrants 1 and 2, when defining the inverse function. The inverse of the secant function with domain restricted to all points in the closed interval 0 to pi, except for the point pi over 2, is called the inverse secant function and is shown in the following graph. Note that the domain of the inverse secant function is equal to the range of the secant function, which is equal to the union of the intervals minus infinity to -1 and 1 to infinity. On the other hand, the range of the inverse secant function is equal to the restricted domain of the secant function, which is the union of the intervals 0 to pi over 2 and pi over 2 to pi. In other words, the range of the inverse secant function corresponds to quadrants 1 and 2. Finally, for the cosecant function, we will restrict the domain to the interval minus pi over 2 to pi over 2, excluding the point 0. The resulting function will pass the horizontal line test, and its inverse will be called the inverse cosecant function. Note that the domain of the inverse cosecant function is equal to the range of the cosecant function, which is the union of the intervals minus infinity to -1 and 1 to infinity. Also, the range of the inverse cosecant function is equal to the restricted domain of the cosecant function, which is all numbers between minus pi over 2 and pi over 2, excluding the value 0. In other words, the range of the inverse cosecant function corresponds to quadrants 1 and 4. This concludes. In this video, we will review trigonometric identities. First, recall that a point on the unit circle corresponding to an angle theta has an x-coordinate equal to cosine theta and a y-coordinate equal to sine theta. Therefore, it is possible to express each of the other four trig functions in terms of sine and cosine. Specifically, tangent of theta, which is y over x, is equal to sine theta over cosine theta. Cotangent theta, which is equal to x over y, is equal to cosine theta divided by sine theta. Secant theta, which is equal to 1 over x, is equal to 1 over cosine theta. And cosecant theta, which is equal to 1 over y, is equal to 1 over sine theta. These equations all represent basic trigonometric identities. An identity is simply an equation which is satisfied by all possible values of the unknown variable. In our first example, we will use these basic trigonometric identities to rewrite the given expression in terms of sine and cosine. All we have to do is rewrite each individual term in terms of sine and cosine, and then simplify. We have tangent theta equals sine over cosine. We have cosecant theta equals 1 over sine. And we have cotangent theta equals cosine of theta over sine theta. We see that the sine terms in the numerator will cancel. This leaves 1 over cosine of theta in the numerator. And dividing by the fraction cosine theta over sine theta is the same as multiplying by the reciprocal of this fraction, which is sine theta over cosine theta. Multiplying these two fractions, we obtain sine theta over cosine squared theta. Another important trigonometric identity is the Pythagorean identity. This identity is a direct consequence of the Pythagorean theorem. It states that cosine theta squared plus sine theta squared is equal to 1. It is easy to see that this equation is satisfied for all values of theta, since any point xy on the unit circle satisfies the equation x squared plus y squared equals 1. From this identity, it is easy to derive two other trigonometric identities. First, if we divide each term by cosine squared theta, we get tangent squared of theta plus 1 equals secant squared of theta. On the other hand, if we divide each term by sine squared theta, we get 1 plus cotangent squared theta equals cosecant squared of theta. In summary, we have the following three Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. These identities are useful for expressing one trigonometric expression in terms of another. For example, from the first identity, we can express sine squared of theta in terms of cosine squared theta, and vice versa. First, solving for sine squared of theta in this equation, we get sine squared theta equals 1 minus cosine squared theta. Next, solving for cosine squared theta in this equation, we get cosine squared theta equals 1 minus sine squared theta. In the next example, we will try to simplify the given expression using the previous Pythagorean identities. First, note that we can replace sine squared theta with 1 minus cosine squared theta. Therefore, the given expression is equal to 1 minus cosine squared theta over 1 plus cosine theta. Since the numerator is a difference of two squares, we can factor it. This gives us 1 minus cosine theta times 1 plus cosine theta all over 1 plus cosine theta. Therefore, we can cancel 1 plus cosine theta, and the expression simplifies down to 1 minus cosine theta. Another important set of identities are the angle addition identities. First, for the sine function, we have that sine of x plus y is equal to sine x times cosine y plus cosine x times sine y. And the sine of x minus y is equal to sine x times cosine y minus cosine x times sine y. Notice that for the sine angle addition identities, the plus signs in this equation match, and the minus signs in this equation match. Also, each of these terms on the right-hand side contains one factor of sine and one factor of cosine. We compare this with the angle addition identities for cosine, which state that cosine of x plus y is equal to cosine x times cosine y minus sine x times sine y, and cosine of x minus y is equal to cosine x times cosine y plus sine x times sine y. Notice that in this case, the signs do not match, and each of these terms contains either two factors of cosine or two factors of sine. From the angle addition identities, it is easy to derive double angle identities. First, for the sine function, we have sine of x plus x equals sine x times cosine x plus cosine x times sine x. Since these expressions are identical, they are like terms and they can be combined. Therefore, on the left-hand side, we get sine of 2x, which equals 2 sine x cosine x. This is the double angle identity for sine. Next, for the cosine function, we have cosine of x plus x equals cosine x times cosine x minus sine x times sine x. Therefore, on the left-hand side, we get cosine 2x, which equals cosine squared x minus sine squared x. This is the double angle identity for cosine. Using the Pythagorean identities, we can also find other double angle identities for cosine. First, if we replace sine squared x with 1 minus cosine squared x, we get that cosine 2x equals cosine squared x minus 1 minus cosine squared x, which simplifies to give us 2 cosine squared x minus 1. Next, if we replace cosine squared x with 1 minus sine squared x, we get cosine 2x equals 1 minus sine squared x minus sine squared x, which equals 1 minus 2 sine squared x. This gives us the following three double angle identities for cosine. Cosine 2x equals cosine squared x minus sine squared x. Cosine 2x equals 2 cosine squared x minus 1. And cosine 2x equals 1 minus 2 sine squared x. Finally, let us apply these double angle identities in the following examples. First, we will try to simplify the expression 2 sine theta minus sine 2 theta times cosine theta. Using the double angle identity for sine, the given expression is equal to 2 sine theta minus 2 sine theta cosine theta times cosine theta, which is equal to 2 sine theta minus 2 sine theta cosine squared theta, which is equal to 2 sine theta times 1 minus cosine squared theta, which is equal to 2 sine theta sine squared theta, which is equal to 2 sine cubed theta. Finally, let's simplify the expression cosine 2 theta plus 1 divided by cotangent theta. There are 3 double angle identities for cosine that can be applied in this case. We will choose the most convenient one, which is 2 cosine squared theta minus 1. That way, when we add 1 to this term, the 1's will cancel. Simplifying the numerator and rewriting the denominator in terms of sine and cosine, we get 2 cosine squared theta divided by cosine theta over sine theta. Simplifying this compound fraction, we obtain 2 sine theta cosine theta, which is equal to sine 2 theta. This concludes our review of trigonometric identities. In this video, we will review trigonometric equations. Let's start by analyzing the basic trigonometric equation sine theta equals 1/2. Our goal is to solve for theta in this equation. More specifically, our goal is to find all values of theta that satisfy this equation. First, observe that the solutions of the equation sine theta equals 1/2 correspond to the values of theta where the sine function attains the value 1/2. This corresponds to the points where the sine graph intersects the horizontal line y equals 1/2. One value of theta where sine attains a value of 1/2 is theta equals pi over 6. This specific value, and only this one, is denoted by sine inverse of 1/2. Because the sine function is periodic, if we add 2 pi to pi over 6, or if we subtract 2 pi from pi over 6, we obtain additional values of theta where the sine function attains a y value of 1/2. Another solution of this equation is theta equals 5 pi over 6. Again, if we add 2 pi to this value, or if we subtract 2 pi from this value, we obtain additional solutions of the same equation. Alternatively, we can analyze this problem from the point of view of the unit circle. There are 2 points on the unit circle with a y-coordinate of 1/2. This one and this one. This point corresponds to the angle theta equals pi over 6. If we add 2 pi to this angle, we get the angle 13 pi over 6. Similarly, if we add 4 pi to this angle, we travel twice around the circle and return to the same point. This corresponds to the angle 25 pi over 6. If we add another 2 pi to this angle, we obtain the angle 37 pi over 6. Observe that the sine of all of these values is 1/2, since each of these angles correspond to this point on the unit circle. Similarly, if we subtract any multiple of 2 pi from pi over 6, the resulting angles have a sine value of 1/2. That is, the values negative 11 pi over 6, negative 23 pi over 6, and negative 35 pi over 6 all have a sine value of 1/2. We can express the set of all angles related to pi over 6 in this way by writing theta equals pi over 6 plus 2 pi k, where k is an integer. This leads to an infinite set of values which satisfy the equation sine theta equals 1/2. For example, when k equals 0, we obtain the solution pi over 6. When k equals 1, we obtain the solution 13 pi over 6. When k equals minus 1, we obtain the solution negative 11 pi over 6, and so on. The other point on the unit circle with a y-coordinate of 1/2 corresponds to the angle theta equals 5 pi over 6. By a similar analysis, all of these values, namely 17 pi over 6, 29 pi over 6, and 31 pi over 6, all correspond to the same point on the unit circle and have a sine value of 1/2. Also, by subtracting multiples of 2 pi, we obtain the angles negative 7 pi over 6, negative 19 pi over 6, and negative 31 pi over 6. Each of these angles also has a sine value of 1/2. The set of solutions related to 5 pi over 6 in this way is denoted by theta equals 5 pi over 6 plus 2 pi k, where k is an integer. This corresponds to another infinite set of values which satisfy the equation sine theta equals 1/2. In summary, all solutions of the equation sine theta equals 1/2 can be expressed in the form theta equals pi over 6 plus 2 pi k, or theta equals 5 pi over 6 plus 2 pi k, where k is an integer. While trig equations usually have infinitely many solutions, in some cases we may be asked to find only the solutions which fall within a specified range of values. In this example, we're given the equation tangent theta equals 1, and we're given that theta is between pi and 3 pi over 2. Under these conditions, we want to find theta. Note that the range of values pi to 3 pi over 2 corresponds to quadrant 3 on the unit circle. Since tangent theta equals 1 and tangent theta is y over x, we're looking for the point on the unit circle in quadrant 3 for which y over x equals 1. This means y equals x, and there is only one point in quadrant 3 for which this is true, namely this point, which corresponds to theta equals 5 pi over 4. Therefore, there is only one solution of the given problem, which is theta equals 5 pi over 4. In this next example, we're given that cosine theta is negative root 5 over 3, and we're given that theta is between pi over 2 and pi. Given these conditions, we want to find tangent theta. In this problem, we can actually avoid finding an explicit value for theta. Instead, we will rely on trig identities to find the value of tangent theta from the given information. First, recall that tangent theta is sine theta over cosine theta. Since we're given the value of cosine theta, we just need to find the value of sine theta. To find this value, we will use the identity sine squared theta plus cosine squared theta equals 1. If we substitute the value minus root 5 over 3 for cosine theta, we get sine squared theta plus minus root 5 over 3 squared equals 1, which means sine squared theta plus 5/9 equals 1, which means sine squared theta equals 4/9, which means sine theta equals plus or minus 2/3. Since theta is in quadrant 2, this means that sine theta must be positive. Therefore, tangent theta equals sine theta, which is positive 2/3, divided by cosine theta, which is negative root 5 over 3. Simplifying this fraction and rationalizing the denominator, we obtain minus 2 root 5 over 5. Alternatively, we may approach this problem using triangle trigonometry. If we ignore the minus sign in this equation momentarily, then we can set up a right triangle in which the cosine of theta equals positive root 5 over 3. Using the Pythagorean theorem, we can solve for the remaining side, which in this case is 2. Then, using this triangle, we find that tangent theta is opposite over adjacent, which is 2 over root 5. To complete this method, we need to add a plus or minus sign here depending on the quadrant in which theta lies. In this case, theta lies in quadrant 2, which means that tangent theta will be negative. This is because the x and y coordinates of points in quadrant 2 have opposite signs. Therefore, we obtain the same answer as before, which is tangent theta equals minus 2 root 5 over 5. In our final example, we will find all solutions of the equation 2 cosine squared theta minus 2 sine squared theta equals 1, which lie in the interval 0 to 2 pi. At first glance, it's not clear how to solve for theta in this equation. A useful strategy for solving more complicated trig equations, such as this one, is to use trig identities to express the equation in terms of one trig function. Here our equation involves both cosine and sine, so we would like to eliminate one of these two functions from the equation. First, let's factor 2 out of the left-hand side of the equation, which gives us 2 times cosine squared of theta minus sine squared of theta equals 1. We then observe that cosine squared theta minus sine squared theta is equal to cosine 2 theta. Therefore we have 2 cosine 2 theta equals 1. Finally, dividing both sides by 2, we obtain cosine of 2 theta equals 1/2. Here our equation takes a more familiar form. In order for theta to satisfy this equation, we see that the angle 2 theta must correspond to one of the following 2 points on the unit circle. 1/2 square root of 3 over 2, or 1/2 minus square root of 3 over 2. This point corresponds to pi over 3, and this point corresponds to 5 pi over 3. Therefore 2 theta must equal pi over 3, or 2 theta must equal 5 pi over 3. More precisely, 2 theta must equal one of the values in this list, or one of the values in this list, where these values are obtained from pi over 3 and 5 pi over 3 by adding integer multiples of 2 pi, as illustrated in our first example. Therefore, if we divide each of these values by 2, we obtain all possible values of theta which satisfy the original equation. While these values represent the full solution set of the equation, we were asked to find the solutions which lie in the interval 0 to 2 pi. The only theta values which lie in this range are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. This concludes our review of trigonometric equations.